Welcome to the Oxygen Alliance YouTube channel, where we bring you videos on installation, maintenance, and various trainings on oxygen equipment and devices. If you have comments and/or questions, drop them in the comment section below or write to us info@oxygenalliance.org. Remember to like our videos, subscribe to our channel, and hit the notification bell.
Welcome to this call. My name is Emmanuel Jauya, and I'm speaking to you live from Lilongwe, Malawi. These calls are brought to you by the Oxygen Alliance, and they come through to your way every second and fourth Thursday of the month. Essentially, they are meant to be a platform where biomedical engineers can share knowledge that would positively impact the healthcare ecosystem. I'm hosting the call from Lilongwe, as I just said, and I would like to know where you are joining us from. So type your location in the chat, and also don't forget to type your email address so that we can keep you informed and update you on upcoming talks. Talking to us today are biomedical engineers from the Global Health Informatics Institute under the OpenO2 initiative. These biomedical engineers have spent a good time in trying to regenerate zeolite. And today they freely share this information. And without wasting much of your time, I now hand over to one Mwawi Lungu, who will be leading the presentation. Over to you, Mwawi.
Thank you very much, Emmanuel, for that introduction. As he has already said, my name is Mwawi Lungu. I'm one of the team members that has been working on this project. So the Zeolite Regeneration project is a project that we have been working on for the past 2 years. And we managed to get a preprint out, and it explains the entire process and all the experiments that we conducted along the way. So this presentation is based on that preprint, which is currently published on a preprint server, and we'll be sharing the link to the preprint in the chat. So please have a look at it when you get a chance. All right, so just to give you an outline of what we'll be talking about today. So I'll give you a brief introduction of the organization, Global Health Informatics Institute. So this is where all the experiments were conducted. We'll also share with you the background, what motivated us to start working on this project, the different approaches that we took, the zeolite regeneration process itself, different components and equipment that we used, the tests that we conducted, and we'll also talk about regeneration of zeolite in a column, which is also one of the things that we tried out. So please stick with us to the end so that you learn more on this project. So let me also take this opportunity to introduce the team that worked on this project. We have Jerry Douglas, Efa Solomoni, Chimwemwe TSE, myself, and Brenda Luhanga. Unfortunately, Brenda is not feeling well, so she is unable to join us for the call today. All right, so to give a bit of a background, the Global Health Informatics Institute started its work in 2015, but we were formally incorporated in 2020. So in 2021, when the COVID pandemic hit, a lot of things were affected and we weren't spared. And this forced us to move into the biomedical engineering space. So previously, our main focus was to develop solutions at the intersection of science, engineering, and global health. But when the pandemic hit, we had to also jump into the biomedical engineering space. So for this reason, we had to introduce the OpenO2 initiative, which is an initiative where we're going in different hospital facilities to fix oxygen concentrators. It is also important to point out that Global Health Informatics Institute is the co-founder of the Oxygen Alliance. So the Oxygen Alliance is a coalition between two organizations, GHII and Sunrise International. All right, now to jump into our presentation today, just to give you a bit of a background, as I pointed out, the COVID-19 pandemic was one of the things that forced us to jump into the biomedical engineering space, and the demand for oxygen that was there highlighted the gaps that were there in various medical facilities. So oxygen concentrators have been and continue to be the main source of oxygen in a lot of low and middle income countries. And as we might be aware, oxygen concentrators rely on zeolite to enrich the concentration of oxygen. So with time, the performance of the zeolite decreases. And when this happens, the zeolite requires replacement. So with the Open-O2 initiative, we visited a lot of healthy facilities where we did a lot of zeolite refilling, which left us with a lot of contaminated or used up zeolite. So we couldn't just throw this zeolite away because to purchase new zeolite, it costs a lot of money. And by then we had accumulated around 1,000 kgs of zeolite, which was a mixture of sodium and lithium-based zeolite. And if you are purchasing similar quantities from the manufacturers, this would cost around $20,000. So this motivated us and it triggered our investigation into the feasibility of regenerating this old zeolite rather than purchasing new zeolite. So one thing to also point out is the process that happens in the oxygen concentrators, for those of you who might not be familiar with how this thing works. So the oxygen concentrator produces pure oxygen in a process that we call pressure swing adsorption. So this is where room air is forced into the seed beds, which contain zeolite at high pressure. And when this happens, the zeolite traps the nitrogen and then lets the oxygen pass through. So with time, the zeolite will accumulate moisture. So when this happens, that's what causes the zeolite to lose its ability to hold the nitrogen. So moving on, I will hand it over to my colleague Effa, who will now talk about the early approaches that we took in this project. So over to you, Effa.
Thank you, Maui, for the wonderful introduction. So this afternoon, I'll be taking you through some of the approaches we had in the early days of the project before we were able to regenerate the zeolite. We experimented with different approaches to try to extract moisture from the used zeolite, of which some of the approaches brought in improvement in the performance of the zeolite, whilst others did not work. Some of the approaches are the use of heat and dry airflow. We also tried to use vacuum only. We tried to use dry air only, as well as the use of heat and vacuuming at the same time. Going ahead with the one of the approaches was the use of heat and dry air. In this approach, compressed air was passed through the refrigerated air dryer. We modified a portable AC conditioner. We modified the portable air conditioner to serve as the dryer. This dry air was supplied to the drum where it was heated and then passed through the zeolite, which was placed on a fine mesh wire inside the drum. We also had a humidity sensor that was placed on top of the drum to monitor the humidity of the air coming out of the drum. Here are the materials we used during the zeolite regeneration process. To your left is a box containing copper pipe. where air from the compressor is passed through to allow condensation of the water in the air to take place. The middle picture shows a fine fins, which is the evaporation side that allows air that was responsible for cooling the copper pipe to reach a freezing point to enable us to cool the air in the copper pipe. The picture at the right shows the drum that contains the zeolite. In this approach, we carried out a roughly 10 tests, of which we had regenerated zeolite of different types of lithium, of different types, either lithium based and sodium based. Before the experiment, we tested the performance of the two kinds of zeolite in a concentrator, and it was 79% for the lithium based, whilst sodium based was at 47%. After regenerating the zeolite, the performance of the lithium based decreased to 57%, whilst the one for sodium based increased to 52%. In this kind of approach, we had a couple of challenges, of which one of them was the ice buildup on the fins of the evaporator within 30 minutes into the experiment. This was due to lack of the control mechanism to prevent condensation or ice buildup on the fins on the air conditioner we were using. We also had a problem with the humidity of the air which was coming out from the dryer. That is, we only managed to produce air that was 27% of humidity. Another problem which we encountered was the burning out of the zeolite. As you can see on the picture down there to the right, the zeolite was burnt. Moving on to another approach was the use of vacuum. Vacuum drying is a common method used to remove moisture from various materials, including zeolite. In this approach, vacuum pump was connected to one blade of the sieve base to suck out the moisture from the zeolite. However, we noted that the effectiveness of vacuum drying alone in removing moisture from zeolite is very low to improve the performance of the zeolite when put back in the oxygen concentrator. This led to the conclusion that the zeolite was not really regenerated. Another approach was the use of dry air only. In this approach, we used the same system used during heat plus dry air process without the heat. We carried out several tests. One of the experiment was run for 1 hour 30 minutes. That is letting dry air to pass through the zeolite on the mesh inside the drum, but unfortunately, the performance of the zeolite did not improve. Rather, it went down from 49% to 44%. As you can see, the graph right there, the one in red, it's the graph of the humidity of the air coming out of the dryer, whilst the blue graph is the humidity of the air coming out of the drum. This led to the conclusion that the zeolite was absorbing most of the moisture that was left out from the dryer. Moving ahead, we tried to use the heat and vacuuming at the same time. When we switched to heat and vacuum approach, we abandoned the mesh as a place where we put the zeolite. Rather, we repurposed the refrigerant tank to act as a vacuum tank. That allowed us to suck out the water vapor released during the heating process. Without instant vacuum, the released vapor has the ability to damage the zeolite. In this approach, we also used a PID temperature controller to control the heat being supplied to the tank containing the zeolite. In this kind of approach, we carried out several experiments, mostly with the 515 devil beast concentrator zeolite. Initially, we took a 25% zeolite, and it was heated for roughly 27 hours. After that, the performance increased to 69%. After all these several attempts to regenerate zeolite, by the end of 9 months, we were finally able to regenerate zeolite. The regenerated zeolite has been tested under realistic conditions. To understand the better current approach, Chimumutius will take us through this. Over to you, Chimum.
All right, thank you so much, Efa. So before we start discussing about the zeolite regeneration process, I want to mention here that our goal was to develop a process and a minimum viable product for a device that could be used by biomedical engineers. These biomedical engineers could be working in a central and district level hospitals to regenerate zeolite in volumes that are commonly used in oxygen concentrators. So now to talk about the regeneration process, we have combined approaches from various sources found in literature and test them in different combinations to determine their effectiveness. So based on our current findings, we have developed a reproducible process for regenerating zeolite in batch sizes that are commonly found in medical oxygen concentrators. That is 1.6 to 4 liters of zeolite. So this process, as I said, can be done by biomedical engineers in context of low and middle income country settings. So to regenerate zeolite, we use a combination of heat, vacuum, and dry air exchange to extract moisture from underperforming used zeolite. So as you can see in the graphics, we have a dry air source. This dry air source is modified from an oxygen concentrator that is producing less than 1% relative humidity. And then we feed this dry air into a crucible that contains the zeolite. So this crucible is under heat. We're giving it 550 degrees Celsius. Between the crucible and the heat source, we have a thermocouple that is connected to a PID controller. At the same time as while we are introducing dry air and heating, we are also vacuuming, that is sucking out the air from the crucible at a level of minus 21 inches of mercury vacuum. And this air is also introduced at approximately 20 liters per minute. Moving on. We constructed an experimental jig, as you can see in the picture, through 1 to 7. This jig comprised of a heating chamber which housed a removable airtight crucible within which zeolite was placed. So number 3 there is the drum where zeolite was placed inside a crucible. And number 1 is the dry air source, a modified oxygen concentrator. And we're heating it at 550. The electric heating element was installed at the base of the heating drum. So dry air is generated using a modified oxygen concentrator, as I said, with zeolite replaced with an alternative desiccant in the seedbed of this concentrator we are talking about. And the dry air was introduced in the crucible at a rate of 20 liters per minute. So the duration for the process ranges from 3 to 6 hours, depending on the quantity and also the moisture content of the zeolite prior to regeneration. So vapor from the crucible is sucked out at a pressure, as I said, minus 21 inches of mercury using a vacuum pump. The vacuum pump you can see in 3. We have a water trap between the crucible and the vacuum pumps. 4 you can see there. Just between 4 and the 5, the vacuum pumps, we have a pressure transducer, a pressure sensor, an electronic one, and we also have an analog pressure sensor. These sensors are used as redundancy just to see if, in case anything goes wrong, we can check on the other to see if they're giving the same results. So the humidity of the stream of air coming out of the vacuum pump is monitored to determine when the regeneration process is complete. So through experimentation, we have determined that zeolite is adequately regenerated when humidity drops below 35%. Moving on. So now I want to talk about the results of the regenerated zeolite. So we are able to fully regenerate zeolite to a level where it is capable of generating oxygen concentration of 95.6% at a rated flow rate when reinstalled into a functional oxygen concentrator. So I also want to mention here that we have focused on achieving regeneration within a few hours so as to make process convenient for biomedical engineers repairing oxygen concentrators. So one other thing I want to mention that there are several factors that affect time of regeneration of zeolite. So we have achieved regeneration at temperatures as low as 350 before. But however, if you are regenerating at this lower temperature compared to the one that we normally use, 550, you need high levels of vacuum, and also you would need to increase the flow rate. So of the dry air, that is. So increasing the flow rate of the dry air reduces generation time, but however, you sacrifice or you pay with the vacuum. So the vacuum reduces at this rate. So for a successful regeneration process, you need at least to balance a combination of dry air exchange, vacuum, and also heat. Moving on. During our regeneration process, we use humidity sensors and electronic pressure transducer connected to a microcontroller. So the results we get are displayed in real time on a serial monitor. We also log these results so that we can analyze them later. So as for the testing of the zeolite, zeolite is put back in a pair of sieve beds after regeneration. The sieve beds then are installed in a fully functioning oxygen concentrator. Then we measure the oxygen purity using both ultrasonic and chemical analyzers at the rated maximum flow rate of the oxygen concentrators. So we use the ultrasonic and also the chemical analyzers just to double check that we're getting proper results and there are no issues with the measuring instrument. So now I want to move on about the components and equipment used in the zeolite regeneration process. So I'll start with the crucible. This is the tool that houses the zeolite when during regeneration. So to create a sealed environment within which we could create a vacuum or heating the zeolite, we repurposed and made several modifications to a steel refrigerant cylinder. So the cylinder was cut in half to facilitate the installation of a wire mesh, separating the upper and lower part of the cylinder. So in pink there is the cylinder, and in the graphic just next to the cylinder, you have the wire mesh and half of the refrigerant tank that we repurposed. So the cutting and installation of the wire mesh enabled us to suspend the zeolite, distributing it evenly over the entire surface. So this in a way helped to minimize the depth of the zeolite and reduced any moisture released from the lower layers of the zeolite to be reabsorbed back above this by the zeolite above it. So I also want to mention here that the gauge of the wire mesh was fine enough to prevent any zeolite from passing through while still allowing air to go through it. So once the mesh was installed, the two halves of the cylinders were welded back together. You can see at the picture below that they welded back together the halves of the cylinder. Two copper pipes were connected to the crucible, one leaving the crucible and the other one coiled around the crucible, and it is connected at the base of the crucible. So this is the one, the coiled one was the one that was introducing dry air into the crucible at a relative humidity of less than 1%. So the second pipe was positioned at the top of the crucible so as to allow air to be evacuated by the vacuum pump, which was also picking up moisture that was released from the zeolite. Lastly, we installed a 14mm threaded access port at the top with a bolt installed and a higher temperature washer to prevent any leakages, and also this in a way provided a tight seal. So in this configuration, zeolite was poured into the crucible before regenerating by using a funnel. But when we want to remove it after regenerating, we just invert the crucible and allow the zeolite to go out. So we move on. So now I'll talk about the heating methods, how we generated heat. So to regenerate the zeolite, we needed to heat the zeolite as quickly as possible while not exceeding 10 degrees Celsius per minute in temperature. So, and to maintain this target temperature within with a minimal power consumption. So to achieve this, we enclose the crucible within a steel drum, roughly 94 centimeters tall and 38 centimeters in diameter. So we installed a heating electric element, as I said, area at the base of this drum that was inside. You can see in the picture there, they're covered by some white stuff. I'll explain what it is. So inside that, there is a drum that houses the heating elements and also where we put the crucible. So this drum was then placed inside a second larger drum, the one that's outside, you can see right there. This drum measured 86 centimeters tall and it was 57 centimeters in diameter, with a gap approximately 10 centimeters between the drum walls. This gap we filled with ceramic fiber blanket insulation to minimize heat loss. So now I want to talk about the types of heating elements we experimented on to achieve the temperature we wanted, that is 550. Firstly, we worked with convection even tubular heating elements. Then we went on and tried ceramic heating loads. Later on, we tried camphor wires and heating elements from a cross dryer. Later, and finally, we experimented with silicon carbide loads. So to begin with, we firstly use convection heating elements that are commonly used in ovens. They are fast, efficient, and they allow even heat distribution. So in our area experiments, we heated zeolite up to 100 degrees Celsius using a 3,400 watts heating element from a convection oven. However, as we increase the temperature, we determined that these elements will not operate above 450. So this led us to investigate a different type of heating element. So this led us to try to use camphor wires and also a heater from a clothes dryer. So to mitigate the issues, we faced with the convection oven heater, we switched to using camphor wires, which we have previously seen used in homemade kilns. So unfortunately, at the temperature we needed, the wires expanded to a point where the coils would surge or touch each other and creating a short circuit. So when this happened, we tried to use heating elements from a clothes dryer. So we also noticed that the coils on the elements changed shape after using it for several hours. Later on, we also noticed that the wires shorted out. So we had to abandon the dryer from the heater from a dryer rather. So we went on to experiment on these locally available ceramic heating loads. So as I said, these are locally available. So one of the locally available heating elements, this is made from a wire wrapped around a ceramic rod for support. These elements were able to achieve temperatures in excess of 550 degrees Celsius. So we constructed a jig to hold these elements. As you can see, they are inside a drum. So using 6 elements, it took only 40 minutes to reach 550. So to maintain the target temperature, we used an off-the-shelf PID controller. So we placed a thermocouple between the PID, crucible and the heating elements. And also for the thermocouple, we had to shield it from radiation so as not to peak erroneous temperature readings. And finally, we experimented with silicon carbide loads. Silicon carbide loads are a popular choice for high temperature heating application due to their unique properties. So silicon carbide loads have higher temperature capabilities up to 1,800 degrees Celsius. Another advantage is in terms of longevity and also durability. These elements can run for thousands of hours to several years without degrading. So they are also fast in heating and cooling. One of the main disadvantages for these silicon carbide loads is that they are very brittle and fragile in handling. They are very expensive, and also they require a dedicated power control system due to their nonlinear nature in drawing current. So moving on, I'll talk a little more about the vacuum approaches we used. Just as a reminder, as we discussed earlier, that for successful regeneration of zeolite, we need a combination of dry air exchange, vacuum, and also heat. So for the vacuum approaches, we experimented with an industrial grade belt-driven watch vacuum pump, which we connected with three-phase motor. Later on, we switched to a single piston diaphragm pump, which is just DC power. Then we modified oxygen concentrator compressor to work as our vacuum pump. So for a start, we start with the three-phase industrial grade watch pump. When we started experimental process using a laboratory quality-driven vacuum pump, as you can see in the graphics, we were able to achieve a vacuum of about minus 27 inches of mercury. One thing I want to say here is that this class of vacuum pump is very expensive. It can go above $1,800 US dollars, but this one is very reliable. So, however, as the pump is all lubricated, we had to remove all the moisture from the air before it even reached the vacuum pump. As we discovered that moisture would emulsify the oil inside the vacuum pump. So we noted that air removal was, the moisture removal was very problematic when we were using this vacuum pump, and the moisture would find its way back to the watch vacuum pump. So we opted to try a different pump that would tolerate the moisture. So this is the time when we went to a single piston diaphragm vacuum pump. We switched to a diaphragm pump. However, this pump was only capable of achieving minus 17 inches of mercury. So we needed up to maybe minus 27.5 or up to minus 29 inches of mercury. So to increase the vacuum, we pressed two vacuum pumps in series, and we were able to achieve minus 25 inches of mercury. So another thing we noted was that after 50 hours of use, we observed that the reed valves in the diaphragm pumps were quickly deteriorating, and it was causing us to lose vacuum. So we had to look for an alternative that would be reliable. So this is when we finally switched to using a double cylinder compressor. This design is commonly found in oxygen concentrators. One of the oxygen concentrators where it is found is the DeVille base 515 concentrator. So to increase the vacuum level, we converted from single stage vacuum pump to a two-stage vacuum pump. So we had to do some replumbing. We removed the two cylindrical pipes, as you can see in the graphics there, and we had to close the holes that these pipes left with hex plugs. Then we connected the outlet of one cylinder to the inlet of the other just to increase the vacuum. So reaching this far, I'll ask my colleague to continue with the mechanisms of regenerating dry air. Thank you.
Okay, thank you, Chimwemwe. As we have already learned that dry air is very essential to zeolite regeneration, let us now discuss on how dry air for zeolite regeneration is generated. Dry air can be generated either through the use of refrigerated air dryer or using desiccant. I will talk more about a approach used in dry air generation, which is using refrigerated air dryer, whilst my colleague Mawi will discuss more on dry air generation using desiccant. In the early days of this project, we used the same refrigerated air dryer that we modified from a portable air conditioner, but with few more modifications. We removed the evaporator that comes with the air conditioner and replaced it with a coil copper pipe. Refrigerant copper pipe was soldered direct to the air pipe to enhance heat transfer. This approach reduced the air humidity to as low as 0%. But this approach had challenges. First of all, we were producing air with very low flow rate. We also had a problem in ice buildup inside the air pipes that led to blockage of the pipe, resulting to no production of the dry air. Now let me let my colleague Maui to talk through about the desiccant approach. Maui Lungu.
Thank you very much, Effa. So as she has explained, we tried two different approaches on reducing the relative humidity. And the second approach that we tried out was the use of dry air. So we did some research, and most paper on the internet suggested that using nitrogen or helium as a source of dry gas is ideal. So we saw this would be, when we looked at this, we saw that this would be a problem, since the solution that we were trying to develop was meant for low and middle income countries. So most facilities still wouldn't be able to afford purchasing helium or nitrogen as a source of dry gas. So we also came across another paper which showed that dry air was effective. So we tried using dry air instead, and we were able to achieve a relative humidity which went down to 6%. So moving on to the next slide, we also came across a couple of designs, and with these designs were designs of regenerative desiccant air dryers. So when we examined the designs, we saw that they were similar. There were similarities with oxygen concentrators. So we took an oxygen concentrator, tested the outputs, and then we found that the relative humidity that was produced by an oxygen concentrator was less than 1%. So this suggested that the moisture was being removed by the zeolite, and in a way it was regenerative. But then we could not use an oxygen concentrator as it was as a source of dry gas, because it was largely composed of oxygen. So this was not ideal, since this approach required using heat. So what we did was we had to exchange the zeolite that is in the concentrator with activated alumina desiccant. So if you can go to the next slide, you'll see that there is an image of an oxygen concentrator which we had modified, and in the seedbed canisters, instead of having zeolite, we replaced the zeolite with an activated alumina desiccant. So we used an air sep intensity 10 oxygen concentrator as a source of dry air. So with this, we were able to achieve -1% of relative humidity, and this was giving us roughly 25% of oxygen. So these were levels that we could easily work with. So we also tried to experiment using rice to remove the moisture. So we thought of using rice because this is readily available in almost everywhere, and most low and middle income countries would be able to afford this. So we tested it out, and we found out that it took several minutes to achieve low relative humidity, and the lowest we could achieve was 4%, so which was still not down to the levels that we wanted. So we had to abandon this idea. Moving on. So we then came across the desiccant, and we used the desiccant. We were, as I explained, we were able to achieve -1%. But then we came to observe that after 5 months, the desiccant would then begin to underperform. This was because it now had accumulated a lot of moisture. So we needed to find a way where we could also regenerate the desiccant without actually damaging the structure. So we also did a bit of research again, and we came across some information which indicated that we can regenerate the desiccants at a max temperature of 350 degrees Celsius, and we needed to have a temperature ramp up of 50 degrees Celsius per hour, otherwise we would damage the structure of the zeolite. So we tried this out, but then it did not give us the desired results because the desiccant was still underperforming. So we then decided to just use the same process that we're going for when regenerating the zeolite. And when we did this, we managed to regenerate the desiccant to a level where it was capable of producing less than 1% of relative humidity again. So in the image on the slide deck, you can actually see A is the desiccant, which has been saturated with moisture, and then B is the desiccant which has been regenerated. So you can clearly see the color difference there. The one with the moisture is a bit darker, and the regenerated desiccant is a bit brighter. So this is what we are using currently. Moving on. So we also tried to regenerate zeolite in a column, as this was also one of the methods that we came across when we were doing our research. So we did an experiment with this, and what we did was we tried to regenerate zeolite while it's still in the sieve beds, just to have that column. So several observations were made, and the biggest challenge that we have was that when the moisture from the bottom layers of the zeolite was being removed, it would rise up the column and then just get reabsorbed at the zeolite at the top of the column. So this meant that in order for you to remove all the water from the zeolite, you had to run the test for longer. So yeah, this wasn't the best approach, as it was taking a lot of time. So we therefore just settled on having zeolite on a flat bed to avoid the reabsorption of the moisture on the next layers of zeolite. So next, we had to do some longevity tests now after running the experiment, seeing that the zeolite that we had regenerated was producing high purity oxygen. We had to run some extensive tests just to make sure that the effects of regeneration were permanent. So what we did was we used 4 different concentrators of 3 different models. So we had a DeVilbiss 515 and a Longfian J5, which uses sodium-based zeolite, and we had 2 DeVilbiss 525 model concentrators. So before running tests on these machines, we had to make sure that they were performing above standards. So what we did was we refilled them with new zeolite that we purchased from a supplier, and then tested them out. And once we made sure that we saw that they were performing above standard, we then fitted them with the regenerated zeolite and started the experiments. So at the time when the preprint was being published, the J5 had run for 1,995 hours, producing 92% oxygen purity at 5 liters per minute, which is still way above the 82% minimum requirement by the WHO. And the DeVilbiss 525 had run for 1,573 hours, producing 95.6 at 5 liters per minute. So you can see that this clearly shows that the effects of the regeneration had stuck to the zeolite. So next, lastly, I will talk about the benefits of regeneration. So the first benefit is that on-site regeneration is usually more cost-effective in the long run compared to importing new zeolite. So if you are shipping zeolite from another country, you can incur high transportation costs, import taxes, and different other fees. which can significantly increase the overall expenses. And when the COVID-19 pandemic was at its peak, this was also one of the biggest challenges. There was high demand of zeolite and the prices just went crazy. The second benefit is logistical simplicity. So managing logistics of importing zeolite from another country can be complex. As I explained, with the COVID at its peak, this was a very big problem. So managing logistics involves customs clearance, shipping, handling procedures, different other paperwork. And so on-site regeneration eliminates these complexities and simplifies the replacement process. And the other benefit is that it gives back control to biomedical engineers. So since the process of regeneration takes less than a day, it makes the feasibility of getting a broken oxygen concentrator back into the field again more attractive to a biomedical engineer. So right now we have a minimum viable product which is able to achieve regeneration. So the next steps is that we are working on now making the whole device compact so that it's all housed into one unit. As you saw in the images when Chimwemwe was presenting, we had different parts laid out. So we'll try to compact all that into one design which can be easily reproduced. So this is all that we had prepared for you. I'd like to thank you all for hanging back and listening to the presentation. So if you have any questions, we are happy to take those questions. But before we take on the questions, we prepared a poll for you. So I am going to launch that poll and please just respond to it. So the poll is mostly targeting biomedical engineers. So the poll says, do you think the ability to regenerate zeolite at your health facility would be of use? So please just respond to that poll. If you are unable to access the poll, those of you who are joining us from your computer, the icon on the bottom right is the activities button. When you click on that, a window opens up where the polls menu is one of the listed options. If you are joining us from a mobile phone, then you click on the menus option where a window will open up and the activities button is one of the listed options. When you click on the activities button, you should be able to access the polls menu. So while people are voting, I will now hand it back to Emmanuel to take us through the Q&A session. Thank you.
Thank you very much, Maui, and thank you very much, the whole team. This has been a very educative session and we have really learned a lot. But as Maui has hinted on, we give you now a chance to ask questions and give us your comments. So here's what we're going to do. As you are voting, also you can just write your question in the comment box, or alternatively, you can raise your hand and I'll mention your name so that you can ask the question. So over to you, our audience. All right, so we start with Ojen Mungu. You can unmute yourself and speak.
Thank you, colleagues. I think this is a very wonderful innovation coming up. We can't wait to see it running and we're able to assess. Now, my question is, how long do you think you are going to take to come up with a compact system that can be used for regeneration process? Thank you.
Thank you very much. Our team, we have a question. Anyone who wants to take it?
Yeah, thank you for that question. So as I explained that we have many other components which we had to piece together in order for them to work together. So we are tackling one component at a time. So it might take a bit of time to get some of the things compacted because we still need to experiment on a couple of bits. But as the device is right now, it's something that you can be able to reproduce it and should be able to achieve regeneration. So yeah, I think that's how I can respond right now. I don't know if the other team members have a different response or what they might want to add to that.
Thanks, Maui. I'll just add to that. So as Maui had pointed out, we've adopted this modular approach where we've essentially got the crucible, we've got the vacuum system, we've got the dry air system, and then the control system. So we're really trying to optimize each component individually, but we certainly hope that within the next 6 to 12 months, we'd have something that we can get out there. We intend to pilot this in a few selected sites just to see how it's working, get feedback from the users, and we'll continue to iterate on the design.
Thank you very much. I hope that addresses your question, and you can always reach out for further details. But for now, let me take the hand from Geoffrey Barras, and after that, we can take a hand from Bifaso Kaya. Geoffrey, you can unmute yourself and speak to us, please. Okay, maybe we move forward. Bifaso Kaya.
Okay, thank you for the speaks. Hi, everybody. Firstly, congrats for this wonderful project. It is a good innovation, and we think that it will be a good in the future. We are going to regenerate our zeolite. So my question, I would like to know if it is possible to regenerate a zeolite of a PSA, or it's just for a concentrator. Thanks.
Thank you very much. Our team, can you take that? Can we use this process to regenerate zeolite for a PSA plant, or it's just for oxygen concentrators?
So to answer your question,
no,
right.
Go ahead.
Go ahead, Jay. All right.
No,
so,
go ahead.
All right. So now our focus was regenerating zeolite in batches that are commonly used in oxygen concentrators. But with the system, you can regenerate zeolite used for PSA plants, but you need to use like a bigger crucible, vacuum pump, and also the dry air fluid. But with the very same setup, you can regenerate zeolite, but it will take you days on end to regenerate zeolite. Maybe you can approximate to 20 days or 30 days while you're doing the regeneration so that you can put back the zeolite in the PSA plant and make it work. So I hope that answers your question, or Jerry, you may want to add.
No, I think you've got it there. So the volumes obviously are much bigger. We might have 4 liters of the smaller zeolite, ranging from 0.4 millimeters in diameter to 0.8 millimeters in diameter. This is the common size used in the oxygen concentrators, whereas in the PSA plant, it's a larger size granule, roughly 3 to 4 millimeters in diameter, I believe. But the process is essentially the same. The moisture is adsorbed into the surface of the zeolite, and the same process of vacuum, heat, and airflow will essentially remove it. Because a PSA plant might have, maybe 1,000 kgs of zeolite in it, if you had to run this through 4 kgs at a time, it's going to take a very long time. So you would need to invest in a much larger infrastructure. You do not necessarily need something that does 1,000 kgs in one shot. You could also break it down into batches of 50 kgs or 100 kgs. Hence the comment from Chimwenwe that it might take 20 days because you're essentially regenerating it in batches. Thank you.
Thank you very much. We acknowledge to receive questions in the chat, but then those came after Ray Munyaka. So Ray Munyaka would go first, and then we'll read out the questions. Ray, you can come out of mute and speak.
Hello?
Yes, but you may wish to be closer to your device.
Okay, I hope I'm clear now.
Yes, very much
My name is Ray Munyaka from Kenya. My question is more on cost effectiveness and the energy efficiency of the unit. And then the second one comes on sustainability of the unit. Are there any waste from the unit? Does the unit pose any environmental risks? And on the third point, okay, I guess the two of them can serve me right.
Thank you very much. Dr. Jerry, would you want to take these ones?
I think I'll start, and then the other colleagues can add on this. So in terms of energy consumption, you mentioned in the paper, we do a small calculation just to look at how long it runs for, how many watts of power it consumes, and what the cost of energy is in Malawi. And I think it takes less than $3 in electricity to regenerate a batch large enough for an oxygen concentrator. We know, of course, that the cost of zeolite is in the $40 or $50 per kg range. So so this is an expensive proposition to buy it. The electrical cost is negligible, but then the other running costs, obviously the amortization of the cost of the equipment. So at this point, our target is basically to make this solution affordable so that for a typical, say, district-sized hospital that may be maintaining concentrators both for the hospital and for the surrounding health centers, that team of biomedical engineers may be supporting, say, between 50 and 70 concentrators, and that they might have to regenerate maybe once every 3 years. Our target would be to say, if you were not regenerating and you had to buy zeolite over that period of 3 years, how much money would you spend on zeolite versus if you bought this piece of equipment and you were regenerating, even after you've paid off the cost of the equipment, it should still be a net positive gain. So it should be cheaper to regenerate than it should be to continue to buy zeolite. In terms of the environmental impact, it doesn't generate any harmful side effects as far as we know. So I think from that side, I don't think there's any environmental impacts. Let me hand over to my other colleagues and see if they have anything to add.
That's all, Jerry. I think you have explained it well.
Another question. Thank you very much. And we have questions in the chat. I've seen the hands, I'll take them, although our time is running out, but we'll try to squeeze in. So the first question reads, how many times the same zeolites? I guess how many times can you regenerate the same zeolite? And there's also another one, considering the fact that the low to middle income countries are the major targets, is there any intention to sell the product after completion? If so, how much? Then we'll go with the others, but can you attend to these two questions? Thank you.
So I'll answer about how many times you can do the regeneration. Looking at the time we've been doing regeneration, we started like 16 months ago, if not 17. But we've only been able to achieve full regeneration about 7 months ago. So our test right now, we're learning the longevity test. We haven't had issues where this zeolite went bad, like deteriorated, so that we take it back again and test it. We are just waiting for the zeolite to go back again, and then we do the test. As of right now, we haven't done the test where we hit the zeolite again. So this will later be answered when we do such tests. So thank you for your question. Maybe Jerry or Mo, you want to add in some more info?
I think maybe just one of the comments is that we have read in the literature that when you exceed 350 degrees Celsius, you can potentially damage the zeolite. So we are obviously doing this at 550 degrees Celsius. And this is extremely hot. Remember that aluminium melts at 660 degrees Celsius. So we're working at very high temperatures, but we have not seen any degradation in performance of the zeolite, even though we are using the 550. It's very possible that there may be a cumulative degradation. So after regenerating for 3, 4, 5, 6 times, it might deteriorate to the point where it ceases to absorb nitrogen in the way it needs to. But because we haven't had regenerated zeolite there long enough to be able to cycle it a second or a third time, we really don't have any any answer on that at this point. Just to speak to the other question about selling it, I think I made the comment earlier that we we definitely want to get this out there. We think that this will be a useful product for people at the district and central hospital level, and we would essentially set the price to the point that we would make it affordable based on the quantity and volume of zeolite that we would expect those hospitals to regenerate. So we don't yet know what that price is, but that'll be kind of like the pricing model on this.
Thank you very much. So before I take the hands, let me just finish the questions in the chat. There's one from Mulugeta Mideksa, says simplicity of the design to be transferred in income countries. I guess maybe it would sound, though, would you simplify it further, or how do you think it is simple to transfer it between countries? And there's another one. This is from Dixon Mutoka. My question is on storage of the regenerated zeolite before use, considering their high affinity to moisture. So you have regenerated and you want to transfer and use it. How do you store it? I think that's the question. Thank you.
Yeah, so to respond to the first question on the simplicity of the design and how it can be transferred in low and middle income countries. So this device is targeting low and middle income countries, as I pointed out during the presentation. So when we finalize and optimize everything, this should be something that is best suited for the low and middle income countries. I think my colleagues can add on to that if I have missed something. In terms of the second question on storage of the zeolite, so right now on the zeolite that we have been experimenting on, we have some drums which are airtight when you close them. So that could potentially be one place where we can store the zeolite. But as Chimwemwe said, we have just achieved regeneration the past couple of months. So we are yet to get to a point where we are regenerating high quantities of zeolite. But for the quantities of zeolite that we have regenerated, it has just been straight into concentrators. And if we have some which we have to keep aside, we have Ziploc bags where we are keeping the zeolite.
Thanks, Molly. Maybe I can just add to those comments and address a couple more comments from Mulugeta in the chat here. So we do see this as kind of like a just-in-time solution. You've got a concentrator that needs to be fixed. You're going to empty the sieve beds into the crucible. You'll regenerate. You'll take it from the crucible and you'll put it directly back into the sieve beds, and you've got that concentrator working again, assuming it has no other fault. So we don't anticipate that storage would be necessarily a problem. If, for example, you were doing this for other organizations and you needed to transfer, certainly the models that Maui has mentioned in terms of Ziploc bags or tanks that are sealed with gaskets can certainly work. Mulugeta, you have a question about simplicity of the design to be transferred to low-income countries. Well, let me point out that this was all done in Malawi, which I think is considered one of the lower low-income countries. And all the design is modeled around technologies that our biomedical engineers are very familiar with. So if you're trying to repair an oxygen concentrator, and the device that you're using for generation is actually based on oxygen concentrator technologies, then already you understand it. If you have a problem with the regeneration device, it's basically just like you're working on another concentrator. We use a concentrator for the dry air source. We use compressors from concentrators for the vacuum source, and the rest is essentially just the heating element and the crucible. You had another question about different types of zeolites. I think, you know, a zeolite is a class of material. There are something like 185 different types of zeolite. Now, zeolites are have different affinities for different types of gases. We know that in oxygen generation, the zeolites that we use are primarily zeolites that have an affinity for nitrogen so that we can separate that nitrogen out from the room air. All I can tell you is so far, every zeolite that we have removed from an oxygen concentrator that we have tried to regenerate, we have successfully been able to regenerate those different types of zeolites. Are there zeolites out there that maybe we'll fail on? We don't know at this point, but so far we've been successful with all types of zeolites that we've encountered that are used in medical oxygen generation. I think I've answered all your questions, Mulugeta, but if not, please just repost the other ones.
Thank you very much, Jerry, and thank you, everyone. Our time is 6 minutes ahead of time. We're supposed to finish at 3, and allow me to conclude, but also worth mentioning that if you still have questions and comments, you can reach out to us on YouTube channel, or you can also find us on Facebook. Our user handle is Oxygen Alliance. Alternatively, you can also write to us at info@oxygenalliance.org. Reaching this far, I'd like to thank every one of us for... All right, there's another question, but it's been attended to. Thank you very much, Jerry. I'd like to thank each and every one of us for making it to this call. Let's also note that we have another call coming up next month. That will be on the 10th of August. Make sure to hang around, and those that have not submitted their emails, you can submit your email so we can send you a reminder. Reaching that juncture is bye from us. Thank you.
Goodbye.
Thank you, Teal. Bye.
Thank you, guys. It was great to hear from you. That was a
thank you
for us, the low and medium income countries. If we could do something, definitely it will help very much in our health centers and the rest. Please, go on, keep up. Feel something is a good beginning. Thank you.
Thank you very much for that comment. We'll surely keep you updated on all the progress that we're making.
Sure, thanks.
Thank you very much.